Today we're going to be looking at the first lesson in Unit 2 called Piggies and Pools. So our objective today is, given a numeric relationship, I can correctly choose discrete or continuous in 2 out of 2 problems. Those are new vocabulary words for this lesson. Discrete is probably a new word for you, maybe. Continuous you've probably heard in other contexts, but maybe we haven't referred to it in a mathematical context yet, so we're going to define that today. Here's some things to think about. We've been looking at sequences. When does it make sense to connect the points on a graph? And when does it not make sense? What does it mean for something to be continuous in non-mathematical contexts? What does it mean in general for something to be continuous? So we're going to start out with a story today. My little sister Savannah is 3 years old. She has a piggy bank that she wants to fill, and she started with 5 pennies. Each day when I come home from school, she's excited when I give her 3 pennies that are left over from my lunch money. We're going to use a table, a graph, and an equation to create a mathematical model for the number of pennies in the piggy bank on day n. So we've sort of highlighted the important info here. You notice we started with 5 pennies. She's getting 3 pennies each day. And so we'll write those things down. We're going to start with 5 pennies. It's increasing by 3 pennies, and it's going up each day. So we have several tools we've used for this before. We have a table, we can write an equation, we can make a graph. We know how to do this. This is just our old standard arithmetic sequence. So if we go up day by day, we'll notice she's getting 3 pennies each day. So it goes up to 8, then 11, then 14, then 17, then 20. We know how to write an equation here. This is going to be good old slope-intercept form. For using n instead of x, it'll look like that. M times n plus b. M is our common difference. B is our value at 0. So our overall equation looks like 3n plus 5. We can graph these points. Let's see, we have 0, 5. 1, 8, maybe up here, 2, 11, something like that. 3, 14 is going to be up here. 4, 17, and then 5, 20. And that looks like a straight line, which is what we'd expect for an arithmetic equation, or an arithmetic sequence rather. So question on this. Would it make sense to draw a line in between these dots? What do you think? If we were to draw a line, let's see, let's start at this dot down here and go up to these dots up here. What we'd be saying then is that all of these points in between, all of these points here and here and here, all of these points would be valid. So, like if I drew a point right there, this would say that at half a day, she had 6.5 pennies. Is that true? Is that consistent with our story? Is there even such thing as half a penny? You know, in some times, in previous times, there were such things as half pennies, but not anymore. We've gotten rid of those. We don't have them anymore. And so this number doesn't make sense. 6.5 doesn't make sense there. And also, we're not giving her pennies throughout the day. We just give her one chunk of pennies at the end of each day. So drawing a line here actually doesn't make sense. We would get rid of that line. That line doesn't make sense because all these points in between are not valid. These are not valid points in between. So the answer there is no, it doesn't make sense to draw a line between these dots. Then we have another question. Would it make sense to extend the dots backwards to negative numbers? So come down here and say down here, maybe this one would be -1. Does that make sense in the context of our story? Well, that would mean she had 2 pennies the previous day, and then she was in debt a penny the day before that. We're not taking away pennies from our little sister. That's not very nice. That's not something we would do. So these values, extending the line backwards, also doesn't make sense in this context. These are not part of our story, not part of the context that we set up. So if we have a function that is dots, but it does not make sense to connect them, we call this discrete. Now this is ETE. There's actually another word in English spelled EET, and this means to be quiet or to be subtle about something. This is not the discrete we're referring to. This is the mathematics discrete, which is spelled ETE. And what we mean by discrete in mathematics is that these points are separate. They're not connected. And there's a tip down here. If something is countable, that often means it will be discrete. So for example, number of people, number of days, number of pennies, like in this example, anything that's referred to as number of, that's a good indicator that this is going to be a discrete variable. Now another concept we hinted at a minute ago was the domain. The domain is the values of the inputs that are valid for this function. So we talked about how -1 is not valid and -2 is not valid. Going backwards in the days doesn't make sense. Also in this one, 0.5 was not a valid input because she didn't have different number of pennies for half a day. It only happened in a chunk at 1 day. So all these in-between numbers are not valid either. For this function that we talked about in this example, our domain would be 0, 1, 2, 3, and so on. All these positive integers plus 0. That would be considered our domain. And down here there's a note about the domain would be all positive integers and zeros known as whole numbers, which is abbreviated capital W. I won't be testing you on that in this class. You don't need to remember the names of sets, but just so if you see this sometime in the future, mathematicians do tend to write sets of numbers this way. So natural numbers you might see as capital N, real numbers you might see as capital R like that, whole numbers as capital W like that. You don't need to remember any of that. All you need to know is how to write the increasing integers that are the domain. So 0, 1, 2, 3, ... That will describe our domain in this case. If you remember its whole numbers, that's cool too. Okay, let's look at another example. Our family has a small pool that holds 1,500 gallons of water. I decided to start filling the pool, but it was taking forever. How long was I going to have to stand here? But then I remembered I'm a mathematician and I can actually figure that out. So I checked the flow on the hose and found that it was filling the pool at a rate of 2 gallons every minute. When I had 5 gallons of water in the pool, I started a timer. What is the important info in the story? Well, it's nice that it's all highlighted and colored. So 1,500 gallons of water, that looks relevant. Maybe we'll highlight that. That's the size of the pool. We're getting 2 gallons every minute. That must be our common difference. We're adding 2 gallons every minute. And then we started with 5 gallons. That's when we started the timer. So if we were to set up a table, a graph, an equation again, let's see, we could do the numbers of minutes over here. We started with 5 gallons of water, and we're adding 2 gallons every minute. So we go up by 2 every time. We can write an equation, f of t, because we're using t up here for minutes, like time. This is going to be our good old slope-intercept form for an arithmetic equation. So m times t plus b. M is our common difference. B is our value at 0. Our equation will be 2t plus 5. Same stuff we've been doing in the last unit. We can graph these points, 0, 5, 1, 7, 2, 9, 3, 11, 4, 13, 5, 15. So this again is a straight line. I didn't quite draw those right in a straight line, maybe more like that. But that's what we expect for an arithmetic equation. This is going to be a straight line. It's arithmetic again. If we wanted to answer that question, how long this pool is going to take to fill, we can set this equation equal to the total number of gallons in the pool and then solve it. Subtract 5 from each side, we get 2t equals 1495. Divide both sides by 2. I guess we're going to need to come over here to get a little more room. We get t equals 1495 divided by 2 is 747.5 minutes. That is so long. We'd be waiting forever. Let's see, if I divide that by 60, how many hours is that? That's about 12 and a half hours. That is a long time to be standing around waiting to fill a pool. That hose must be trickling in, right? All right, so we modeled this arithmetic sequence. So we're going to ask the same question again. Would it make sense to draw a line between these dots? So grab my line here again. If I draw a line here now, draw up like this, the question is, does this point make sense? At half a minute, were there 6 gallons in the pool? Or at 1.5 minutes, were there, I don't know, that's probably about 8? Something like that. At 1.5 minutes. Does that make sense? Yeah, it sure does, because water flows continuously. Vocabulary word. Water flows continuously, which means all of these points in between, over time, existed. So at any one of these points, we could determine how much water was in the pool. All of those are valid. So in this case, yes, it does make sense to draw a line in between the dots. It all depends on the context of the story. Okay, and then our next question is, would it make sense to extend the dots backward to negative numbers? So let's see if I can select this line and then just drop backwards. Does this make sense to extend it back here? What do you think? Well, we know that negative values for the pool, like negative gallons, that doesn't make sense. This down here, negative gallons doesn't make sense. We don't even know what that means. Are we like pulling water up from where it didn't exist in the pool? It doesn't make any sense. But maybe these negative minutes make sense because we were filling the pool before we started the timer. This is just where we started the timer, right? Timer starts there. We were filling the pool during this period. So this might actually be a valid region. We could say our function is valid from here forward. So in this case, yeah, we could argue that it makes sense to extend the dots backwards, but only to x equals negative 2.5 or bigger, and no negative y values. Those don't make sense. So we're introducing the concept of continuous here, as you might have guessed. If we are able to draw a line between the dots and they make sense, it makes sense to have those dots, we call it continuous. The graph does not have any breaks or holes. And there's a tip up here. If something is measurable but not countable, that often means it'll be continuous. There are some examples like weight of a child as they grow up, or a height of a tree, right? So a tree grows continuously. It doesn't have big jumps between heights. Or volume of water, like in this problem we're working on here. Volume of water tends to be a continuous variable. So question on this one, what is the domain? We just talked about what the domain is. We said the domain is all valid inputs. And remember, our inputs are going to be our x values here, x. So what are our valid inputs here? We know that 0 was 1. That was our starting value. We know that 1 is 1. 2. All of these integers are. We also said that 0.5 is. That's a good one. And basically any number in between here, right? 0.25, 0.7, any of those numbers in between any of those numbers here. So pretty much anything positive is valid. And then we even said that this region right here, all the way back to negative 2.5 is valid. So we have a really condensed way of writing this because it would be impossible. There are literally infinite numbers to write on this line. We condense this by saying x is greater than or equal to negative 2.5. All the numbers that are bigger than negative 2.5 are valid inputs. Who knew that inequalities would be useful to us? So we're going to pause this video and resume it in a part 2. So these will only be about 15 minutes each. We'll go through a couple more examples in part 2.